Okay, happy Wednesday, everyone. Today is going to be regular lesson day, asynchronous learning though. So first thing I'm going to ask you to do is work on this warm-up 3 problems. So go ahead and pause the video right now, and I'm going to post the solution at about the 20-second mark. So pause the video right now, and I'm going to start working on the solution. Okay, so for problem 1, we're going to solve the triangle. That means we're going to look for, right now we're looking for the length of the shortest side. Shortest side happens to be side AB here. Normally when I solve for triangles, I'm going to want to write down all the information. So I already wrote down measure of angle A is 63 degrees, measure of angle B is 90 degrees. Angle C is going to be 27 degrees, just because they all add up to 90 degrees. Now if I'm looking for the shortest side here, that looks like it's going to be a cosine problem. And I'm going to want to use cosine because I want to use all of the given information so I don't make a mistake. So we'll just say cosine of 63 equals adjacent over hypotenuse, AB over 11. Then to get AB by itself, I'm going to multiply both sides by 11. 11 times cosine of 63 equals side AB. And when I go ahead and plug that into my calculator, make sure my calculator is in degree mode. If I'm using an online calculator, I still have to make sure it's in degree mode. All right, and then I find length AB. Turns out it's going to be 4.9939. Or we could just round it up to 5 if we wanted to and say it was side length 5. Okay, so AB equals approximately 5 centimeters. And that'll be our answer for number 1 on the warm-up. Okay, but whenever we're solving for sides and angles of a triangle, let's use all the given information to try and solve for them. It'll make it a little bit easier to solve. For problem number 2, it says use technology to solve this equation. So we're going to want to graph this. So we're going to graph first y equals x cubed minus x. Then we're going to graph y equals 10x squared minus 50. And finally, we can graph, you might have a calculator that allows you to graph x is greater than 5, or you can just graph x equals 5. But basically what you're going to do is you're going to look for an intersection when x is greater than 5. So basically past that line, if you draw that line, x equals 5 line, you want to find the intersection when it's past that line. It turns out there are a couple solutions before 5, and then after 5, there's one solution, and that's going to be when x equals 9.557. So that's how we would solve number 2, using technology to solve the equation. We have to be good at graphing equations and looking for intersections and things like that. All right, you might need to zoom really far out on this one, or what you do is you just scroll really far to the right with your buttons on your calculator without changing your zoom at all, and you should still be able to capture that point. All right, problem 3 here, calculate all the sides and angles in triangle PQR. So I'm going to go ahead and set this up now. I'm going to pause the video for a second and set it up. All right, so I went ahead and drew my triangle, and I set up the equations. The first thing I'm going to do is I want to look for the third side, PR. Because I've been given 2 sides, I can use Pythagorean theorem, which is a squared plus b squared equals c squared. C is always the hypotenuse, so in this case, that's going to be our 13 squared. And then the 5 can be interchangeable. So we're going to solve for this side, which in this case, we're going to call it side PR. So we'll just say PR squared. So I know which side I'm solving for. So PR squared, it turns out it's going to actually, this is also a Pythagorean triple. So if I were to subtract 25 from both sides, I'm going to get 144. So I know PR squared equals 144. So side PR is going to be 12 meters. All right, and now to set up my angles, once I have that 12 on my triangle, to set up the angles, now I'm going to use SOHCAHTOA. And in this case, I'm going to have to use some inverse trig functions. So for example, I know the 5 and the 13 off the bat, so I'm going to try and set them up using those. So for example, if I did cosine of q, that's going to be 5 over 13. So q is going to be cosine inverse of 5/13. We can use that inverse button on our calculator. And then I can do sine of P equals 5/13, and P equals sine inverse of 5/13. And then I can go ahead and drop those in my calculator and find the missing angles. But I want to use the given information that's going to give me the most accurate answers. And for this one, I end up getting Q is 67.38 degrees, and a measure of angle P is going to be 22.62 degrees. All right, and that covers everything for the warm-up. Now, in class today, we only have one example, so it should go pretty fast, which is why I made this an asynchronous lesson. But this one just talks about a real-world situation. Given the radius of a Ferris wheel planned for Alpha Park is 70 meters, and the theta represents the angle measured anti-clockwise from the x-axis. This is what we were talking about with a standard position angle. All right, this is why we did this thing on Monday about standard position angles. Okay, and it says anti-clockwise, which is the same as counterclockwise. Find all the angles for which the pod P is, and it's going to ask us to do two things. First, when it's a distance of 40 meters vertically above the x-axis, and second, when it's a distance of 20 meters horizontally away from the y-axis. So first thing I want to do for this type of problem is I want to go ahead and sketch my Ferris wheel. So this is where we were practicing on Monday with like circle problems. I can just go ahead and sketch the wheel real quick. It's going to look something like that. Now let's try that again. We'll do a little better wheel. So we'll sketch the wheel. Nice round circle, at least our best attempt at a circle. And what's going to happen is we have the center of the wheel, and we say that the radius of the wheel is 70 meters. So that means you're technically 70 meters above ground here, or whatever. You might be a little higher than that above ground. But anyway, when it goes up all the way, it's going 70 meters higher than where it was. So we're going to look for when this thing is 40 meters above the x-axis. What's going to happen at two places? It's going to happen there, and it's going to happen over here somewhere. Those will be like when it's something, oops, I'm not going to put a point there. So something, comma, 40, and something, comma, 40. We're just looking for when it's above the x-axis. For part B, it's asking very similarly, same wheel, but now it's looking specifically for when it's 20 meters horizontally away from the y-axis. So in this case, part B, it's going to be something similar, but it's going to be like up here somewhere, 20 comma something, and again, negative 20 comma something, because it's going to be 20 meters away from the y-axis, and you're going to form some triangles. All right, and this is where we're going to use our SOHCAHTOA knowledge to solve for this type of problem. All right, first things first on this problem, let's start on the top problem. We know the radius is 70 meters, and we know the height is going to be 40 meters. So if I'm looking for this angle theta here, then what I need to do is I need to set up a sine equation. Sine of theta equals opposite over hypotenuse, 40 over 70. Just like the warm-up, I'm going to go ahead and do a sine inverse problem here. Say sine inverse is 40 divided by 70. Okay, and I'm going to figure out what my reference angle theta is. All right, and what ends up happening when I put this in my calculator, I get 34.8 degrees. So what that's telling me here is that theta is 34.8 degrees above the x-axis, and over here it's also 34.8 degrees above the x-axis. But this question was asking me to find the angle measured in standard position. That's what I was saying right here, from the x-axis. So that means what I'm looking for in reality is I'm looking for the angle that goes all the way around to here. So 34.8 is the rest of the distance 280. So the way I'd find that one is I'm going to say 180 minus 34.8, and I'm just going to round it to 300 significant figures. It comes out 3 significant figures. It comes out to 145.2, but I'll just say that's 145 degrees because we'll stick to 3 significant figures. Another way to prove this is if I were to graph it, which we talked about on Tuesday in class, graphing these functions. Now, what's going to happen with the sine function is our graph's going to go all the way up to 70 meters higher than it was, all the way down to 70 meters below where it was. And while it's on its way to 70 meters, it's going to hit 40 meters at some point. And it's going to hit those 40 meters in a couple different quadrants. At 70 meters is right where it crosses from quadrant 1 to quadrant 2. Now, unfortunately, we don't have an equation that we wrote to properly graph this equation, so it would be really hard to verify this via graphing, but this is just to give you guys an idea. This is what the visual looks like. But I think the best way to solve this equation is by using an equation to set up sine inverse, and then from there figure out, okay, this other one's in quadrant 2, so I gotta do like this 180 minus thing. All right, so the same thing's gonna happen with part B when we're talking about being 20 meters away horizontally. But I guess with part B as well, there's one thing I didn't take into consideration. It's also going to be 20 meters away in the negative direction. I just realized that now. And that's going to happen a couple times here. So there are technically going to be 4 answers for quadrant B. And that's going to happen 4 different times. So we're going to want to find 4 angles for part B here. So this time we're going to do 20 meters horizontally, and we still know 70 is the radius. So we'll set up cosine function. Cosine of theta equals 20 over 70, and then we're going to use inverse functions to solve. And this is only going to give us the answer in quadrant 1, and then we have to be smart about how to find the other answers. So when we do 20 over 70, we'll find our answer of 73.3 degrees. And again, that's going to tell us that in each respective quadrant, we are 73 degrees away from the x-axis. So there's going to be a quadrant 1 answer. That's what this one is. Our quadrant 2 answer, I'm just going to use a little 1. So there's our theta for quadrant 1. Our theta for quadrant 2 is going to be 180 minus 73.3. Our theta for quadrant 3 is going to be, let's see, it's going to be 180 plus another 73 degrees. And our theta for quadrant 4 is going to be 360 minus 73.3 degrees. So that's how we'd find all of our 4 angles for these particular problems. And again, the IB exam loves to go to 3 significant figures, so that's what we're going to try and do here, is just get to 3 sig figs. So we'll do 180 minus 73.3, and that's going to round to 207 degrees. 180 plus 73.3, that's going to round to 253 degrees. And 360 minus 73.3, that's going to round to 287 degrees. Again, just stick to 3 significant figures. It's a good rule of thumb. And we're going to go ahead and box up all of our answers here. Oops, and there's one for 73.3. And that's how you'd solve a problem like this. Now your assignment tonight, 4 problems only. Problem 1 is going to ask another Ferris wheel problem, very similar to what we did on the example. Problem 2 is going to ask you to work on your calculator. Problems 2, 3, and 4. Work on your calculator, modeling these types of problems, and identifying locations and stuff on your calculator. All right, if you have any questions at all, please shoot me an email or set up an appointment for office hours. Thanks so much, you guys.